Thermodynamics of solutions in terms of partial molar quantities, or we can call it thermodynamics of mixing. So first of all, let's suppose we form a solution by mixing at constant temperature and pressure, whereas the number of moles of the substance A is Na, the number of moles of substance B is Nb. So the molar volume of unmixed component A is Wma and for B is Wmb, and the total volume of substance A and substance B of unmixed components is V star. That must be equal to the sum of the molar volume of component A and component B, that is equal to the product of the number of moles of each component and the molar volume of each pure substance. So it is the sum of the product of the number of moles of each component with molar volume of pure substances, and this molar volume is not equal to the volume of the solution that is formed by mixing. But here we are going to discuss that how thermodynamic parameters can be derived for very dilute solutions in terms of partial molar quantities, particularly chemical potentials, using the statistical mechanical treatment. So let's consider substance A having 9 particles occupying particular spaces, and component or the substance B is composed of 16 molecules or the units or number of particles. And when these two components or the substances are mixed, the overall mixed phase have random distribution of the particles of substance A and substance B. So this random distribution is explained by the entropy from statistical mechanical treatment that give the value of entropy in terms of the number of ways how these two types of substances are organized within a mixed solution system. So according to statistical mechanics, the entropy of solution is expressed as K log natural of W, where W is the number of ways, K is a Boltzmann constant. So the W that is the number of ways how the component A and component B is organized into a mixed system, that is given by n factorial over n A factorial into n B factorial. So n is the total number of particles, Na is the number of particles of component A, and Nb is the number of particles or molecules of component B. So if the total number of molecules is very large, so for this case we can apply a standard approximation that is known as Stirling approximation, that is usually applied in the statistical mechanical treatments. Stirling approximation is applicable for very large number of constituents. So for this case, if we apply the Stirling approximation, so we have to simplify this relation, that is the log natural of W is actually equal to log natural of n factorial minus log natural of Na factorial, and it's in denominator, then we have to write the minus sign, and again we are taking log natural of the number of particles of B factorial. So here we are going to apply the Stirling approximation, which gives that the log natural n can be written as n log natural of n. So here is factorial minus n. So according to this approximation, this relation is known as Stirling approximation. So I'm going to apply this approximation to the equation number 3, and according to this approximation, log natural of W is actually equal to the, for this one we have n factorial n log natural of n minus n. For the second one, minus NA log natural of NA minus NA. Again a minus sign, NB log natural of NB minus NB. So now let's simplify this relation. So I have rearranged this equation, and I have moved the NA and NB here. And as we can see that the number of particles of A plus number of particles of B is actually equal to n. So here we have minus n and here we have plus n. So this equation can be simplified as shown here. So here again we can see that this n is actually the sum of NA plus NB, and we can write that this term is actually equal to NA log natural of n plus NB log natural of n plus NB for this term, and this term can be again simplified as NA log natural of n plus NB log natural of n. So according to this addition, we can simplify this equation as log natural of W is actually equal to NA log natural of n plus NB log natural of n Now here we can again simplify according to the laws of log naturals, that is log natural of W. So here we can take the constant outside of the log natural term, and here we have n close to a form that is n over nb. So now we get the equation number 4, and we already have the equation number 1, that is showing the entropy of the solution is given as S is equal to K log natural of W, where K is the Boltzmann constant. Now here we are in condition to replace the value of log natural W, that is the number of ways how the constituent particles are organized into the mixed solution system. So the entropy of the system, it can be written in terms of the equation number 4 is, so if we rearrange this ratio, we can make common the negative sign, that is by inverting these ratios. So maybe you are thinking why we have inverted the ratios and brought this negative sign out. So here we can, if we can see closely the ratios, these ratios are actually the mole fractions, where n is the number of particles of component A over total number of particles. So here is the mole fraction of component A, and the mole fraction of B is given as xB. So overall term within the bracket must having a negative value so that the entropy can be positive, as the entropy of the mixing is always positive because the random distribution of the particles is increased with mixing. And here we get the equation number 5 is an important relation showing the entropy of mixing. Now let's discuss the Gibbs free energy of the mixing. So now let's consider if solution is very dilute to the infinite dilution. So for this case, when the solution is very dilute, that is infinite, up to infinite dilution. So for this case, the heat of solution is considered as almost equal to 0. Why? Because the solute-solute and solvent-solvent interactions remains intact. Solute and solvent interactions are intact. So it means that we are treating the mixing of solution as the ideal case, and for this case the Gibbs free energy of mixing, that is del G, is actually expressed in terms of the heat of formation minus a factor known as entropy factors, that is always negative because of the positive entropy change for the mixing. So for our consideration, we are taking the solution very dilute, an ideal case in which we can consider the solution to up to infinite dilution. For this case, the heat of formation or change of heat is negligible, and the heat that is 0 led to the Gibbs free energy change, that is expressed in terms of the entropy change. And as we have shown, the entropy change for the mixing is given from the equation number 5. So we can write the Gibbs free energy of mixing for ideal solution is actually equal to minus T, and here we have the entropy, that is Na minus K Na log natural of XA plus NB log natural of XB. So here we can modify or simplify the equation, that is K T. So here we get another important relation, that is showing the Gibbs free energy change for the infinitely dilute solution. And equation of entropy change in terms of Gibbs free energy change is given in equation number 7. And the Gibbs free energy change for the mixing is actually the difference between the Gibbs free energy of the solution and the respective components. And for our case, the Gibbs free energy of solution is given written as AB, and for solvent the interactions are considered as AE interaction, and for solute the interactions are considered as BB interactions. And as we know that the Gibbs free energy change is expressed in terms of the difference of Gibbs free energy change from solution and the respective components. So here the Gibbs free energy for the respective components is expressed in terms of the chemical potential. So the chemical potential is actually expressed as the partial molar Gibbs free energy change per number of moles of respective component, keeping the other number of moles of the other components constant at constant temperature and pressure. So according to the chemical potential definition, we can rewrite the equation number 8, that is showing the Gibbs free energy change for the mixing, and we can express the equation number 8, that is the Gibbs free energy change of the mixing, in terms of the chemical potentials. So here we have the value of solution, that is the sum of the chemical potentials of component A and B, and we have the values of chemical potentials of the pure substances, that is for A and for B. These are the pure substances, but these values are for the component that are present in the solution. So here we can again rearrange this equation according to the different parameters describing the change in chemical potential for each component. So here equation number 9 is describing the Gibbs free energy change for the mixing of two components A and B, which is showing that the chemical potentials of the pure components, that is expressed as mu A star and mu B star, have been changed with the value of mu A and mu B, that is for the mixed solution, and the difference of these chemical potentials expressed in terms of Gibbs free energy change, that is given from the equation number 9. So this equation 9 is expressing the Gibbs free energy change for mixing in terms of change of chemical potentials of different components which have been used for the mixing of ideal solution. And here we know that for the case of real solution, the activity is not equal to the concentration or the actual concentration of the solution. It's because of the new interaction that have been developed between the solute and solvent, and various other factors which will be discussed while discussing the conductivity, ionic properties and transport properties of the solution. So here I'm going to just explain that the activity is not equal to the concentration for the case of real solution, but it is actually the product of the activity coefficient and the concentration. And the value of activity coefficient ranges between 0 to 1. For 1, we can consider the solution is ideal. For this case, the activity coefficient is equal to the concentration, that is the actual concentration that have been taken. So we can say that for very dilute solutions, activity coefficient is equal to or nearly equal to 1. It means that the particles of the solute are in monomeric form, and they have been dissociated completely and participating in different properties or transport properties of the solution, like conductivity, mobility, and various other properties of the solution that is relevant to the different ionic properties. And for this case, each component have been isolated and perform its behavior in different experimental measurements, making its contribution that is proposed through theoretical derivations and making it to behave as ideally. So for the case of the activity coefficient, when it is equal to 1, all solute particles are active and in monomeric form, whereas in concentrated solution, solute particles form dimers or trimers or polymers, and they exhibit lower activity. It means they do not participate in various activities of the solution, like the conductance, mobility, viscosity, surface tension, and various other properties. So the overall contribution of the system is less than the number of particles available within the solution. For the case of concentrated solution, when they have mutual interaction or they are making the dimers or trimers or polymers. So for the solutions having activity less than the concentration, so this activity is known as active concentration. And the chemical potential of the component A and component B within the solution is given as in equation number 10 and 11, and these equations are applicable for the solutions when the chemical potentials are similar to active. So in this way we can again express the equation number 9 in terms of the equation number 10 and 11, in which we are going to replace the values of the chemical potentials of the either component within the solution with the chemical potentials of the component A and B in terms of the relation that is showing the chemical potential for pure components. If we observe the equation number 9 star, that is the pre-modified equation of equation number 9, here we have two components which are expressing the chemical potential for the pure substances, that is the Gibbs free energy change for pure substance and the solution. So we have added the value of the chemical potentials of the component A and B within the solution from the equation number 10 and 11. So we get the equation number 12. Here we can see these two components are already as observed in equation number 9 star. So now we have expressed the Gibbs free energy change in terms of the chemical potential of the pure substances. So we can get another simplified form, that is question number 13, which is showing the Gibbs free energy change for this solution or the mixing of component A and B in terms of the mole fraction and the number of moles. And here we can again express the Gibbs free energy change in terms of the mole fraction, and as we know that the Gibbs free energy of mixing is actually equal to the minus T del S for the very dilute solution when the heat of mixing is negligible, and the mixing of solution that led to the change in entropy is actually expressed in terms of equation number 14. So in this lecture we have derived two relations that are showing the Gibbs free energy change in terms of the mole fractions and number of moles, as well as mole fractions and the number of particles. So the equation number 6 and equation number 13 are true for the Gibbs free energy change for the solution, but these are showing the relation for number of particles, that is equation number 6, and the number of moles, that is equation number 13. So here the concentration can be expressed in terms of activity and activity coefficient for the real case. And all discussions are true for dilute solutions.